Well, good morning. Welcome back. And you have started watching videos on Introduction to Machine Learning. And today we are discussing, or rather, continuing our discussion on support vector machine. If we just recap a little bit, so in support vector machine, the main theme is the classification problem has been modeled as an optimization problem, where I have an objective function that is minimize half w square, and this is very simple, quadratic in nature, and subject to constraint which is linear in nature. So as simple as this. And now there are commercially available QP solver. If you provide samples of both the classes, then they can give you the solution of this optimization problem. But we are trying to understand also how we can do it ourselves, right? So we also have seen that this kind of optimization problem, which is known as constraint quadratic optimization problem, can very easily be solved using Lagrangian multiplier method. And what is that method? First, you need to construct a function which you are calling Lagrangian function. How to construct that function? Take the objective function as it is and incorporate the constraint as it is after multiplying with Lagrangian multiplier alpha I. So we have incorporated here with a minus sign. Okay, that means since this is equals to 0, as you know that we can easily do that. That we have done it. There is a theory behind it. Just I am telling how to just visualize that why we have done it. So here also you see that there are as many samples are there, that many Lagrangian multiplier will be there. So this is a Lagrangian multiplier, this parameter, Lagrangian multiplier. And what it will be? Alpha I must be greater than equal to 0. It can never be negative. Okay. And now this function will give me many things. I want the parameter w, so this function is there. I will optimize it. Here it is minimization. And nevertheless, I will just differentiate this with respect to w, make it to 0, and I got w in that process. W is equals to summation of 1 to m alpha I y sub I s I. Then also there is another parameter b, so I need to differentiate that function with respect to b and making it to 0 is giving me minus summation of alpha I y sub I equal to 0. Okay, so we are getting this equals to 0. This is a relation. Okay, and this solution is actually primal solution because our objective function was to minimize it, and primal solution is obtained by satisfying the minimization criteria. Now, for future, what extra we can get, you see, now since we have W, I can put the values of W, I can reconstruct the Lagrangian function like that. So half W square minus, if you do this little algebra, okay, you can see that alpha I y sub I dot s alpha j y sub j is um, sub j. Okay, we have written I j so that to compute in a generalized way the dot product between the samples. Okay, and that's the byproduct we have got. So it is the dot product between. So it turns out that optimization of L depends on the dot product. Okay, so far so good. Now let us try to digest this by taking the example of a small problem which you can do by hand, okay, by hand calculation. Suppose we have two classes, right? So these are the samples, okay. Say they belong to negative class, and there are some samples marked by cross. Say they belong to positive class. And please remember what we have already told, that the level, we have two classes, they're level like this in support vector machine, not 0, 1, minus 1, not. Okay. So these are my samples. So first step, we'll have to actually see who are the support vectors. Okay. For the timing, let us assume that visually we can select them. Okay. As you can see, this could be support vectors are those samples which stays at the boundary. Okay. So where the gutter will be built. Okay. So one such sample I see here to 1, another such sample to minus 1. This is extremely simple example. That is, the two samples belong to negative class, and I see 40 is another sample which belongs to positive class, which are at the boundary. So I select them. Whoever at the boundary are qualified to be selected as support vectors. First, I need to select support vectors, and I have judiciously selected 2, 1, 2, minus 1, 40 as my support vectors. And each support vector has to be assigned with a Lagrangian multiplier. They are respectively alpha 1, alpha 2, alpha 3, for example. Then in step 2, actually we need to augment a bias. This bias is actually, that is in our earlier discussions, regression, logistic regression, we called it like this, making this as always 1, x0 always 1, that is w0. So never mind. So this is our bias B, okay, and we are putting B equals to 1, okay, so that it can accommodate actual value. And we are reconstructing the support vectors like 2, 1, 1 is the bias, 2, minus 1, 1, 4, 0, 1. This is just like we are exploiting the, the constant equation, right? What was our constant equations? If you just remember, it was W dot Si plus B, okay, minus 1 equal to 0, right? So that was what? Huh? Or you can just equals to. Huh? So now if I put the optimum value of W, which just we have got earlier, okay, so this is the value. I am putting this value. So you can actually put in W. And I am just modifying a little bit what to show you that what curly uh, kind of thing means. Okay, I am just putting it or wrapping it inside this matrix. So curly is actually uh, W B and okay. So we have just uh, calling them curly. Okay, so that's it. Is it clear? Because this is also my some parameter. So we have put the parameter inside another parameter in a matrix. That is what we have done here. So we have put, so my S1 becomes S1 curly, S2 becomes S2 curly, S3 becomes S3 curly, just by augmenting bias. And as you know that if you put the values of W, then you will get um, I equals to 1, 2. We have three samples. Three samples we have taken. And alpha j, y, j, and sj equals to 1. And we are just putting them. So for subvector 1, so alpha s1 curly, I have attached alpha 1, okay, and then uh, j equals to 1 to 3. So for this subvector is alpha 1, so just s1 curly z dot product, right, and then alpha 2 s1 dot s1 curly dot s2 curly plus alpha 3 s1 dot s3 s1 s1 curly dot s3 curly, and that sample belongs to, so y is -1, that belongs to -1, so it will be -1. So I got an equation like this. Likewise, I got for another sample which belongs to the negative class, I have calculated alpha 1, and now it is S2. Okay, S2 dot S1 plus alpha 2, S2 dot S2 plus alpha 3, S2 dot S3, all curly equals to -1. So you are getting the rhythm, right? So we are taking a separate vector and then we are calculating this. Okay. So another separate vector which is S3, and we are calculating S3 dot S1 alpha 1 times S3 dot S1 because this alpha 1 belongs to S1, and then alpha 2 is attached with subvector S2, so S3 dot S2, like that. Okay, so very simple. These three simultaneous linear equation we have got, and then just putting the values, what we are getting is alpha 1, 2, 1, 1, and then 2, -1, 1 plus alpha 2, 2, -1, 1, 2, 1, 1 plus alpha 3, uh, alpha 3, 2, 1, 1, and then 4, 0, 1 equal to -1. Similarly, alpha 1, 2, 1, 1. Okay, sorry, this will be, so S1 dot S1. No? So this will be, please, you can also do that. Huh? S1 dot S2. S1, rather, it should be for avoiding confusion, it should be like this. Okay. So S1, S2, S1, S3. Then I should write S2, right? So S2 is 2 -1, 1, 2, 1, 1 plus alpha 2, 2 -1, 1 dot 2 -1, 1 plus alpha 3, 2 -1, 1 dot 4, 0, 1 equals to -1. Okay, and then third equation will be is S3, right? Now S3 is coming into the picture. 4, 0, 1, then 2, 1, 1 plus alpha 2, 4, 0, 1. So rhythm you have got. So there is no difficulties in understanding how simple it is. Dot 4, 0, 1 equals to, remember, it is plus. It belongs to positive plus. Okay. So this actually is giving you uh, simultaneous equation. Okay, so you can just see, just dot product you calculate. 2 to the 4, 5, 6. So 6 alpha I plus 2 to the 4 minus 1 plus 1. So 4 alpha 2 plus dot product. Very easy. 4, 2 fours are 8, 0, 9 plus 1, 9. Huh? So alpha 3, 9 alpha 3 equals to minus 1. Okay. So similarly, 4 alpha 1 plus 6 alpha 2 plus 9 alpha 3 equal to minus 1. And then another equation you will get plus 6 alpha 2 plus 17 alpha 3 equals to 1. So solving this, solve, and you get alpha 1. Uh, by solving you get alpha 1 equals to 3 simultaneous equation, 3 unknown. Okay, simultaneous linear equation. That is the beauty of linear constraint. Okay, equals to alpha 2 equals to, you will get minus 3.25, and alpha 3 equals to, alpha 3 equals to 3.5. So now from primal solution, optimal W will be equals to, so parameter we need, optimal value of the parameter we need, right? So you are actually getting plus alpha 2, 2 minus 1, 1 plus alpha 3, 4, 0, 1. So what you are getting, putting these values, will get something like 1, 0, minus 3. So decision. So you have got the optimal value. Okay, W, and within W0 or B you also got as minus 3. So this is W1, W2, everything you got. So what is the decision boundary? If you just uh, say that we formulated the problem, right, by considering arbitrary decision rule, from decision rule, it follows that W transpose X plus B equal to 0, right? So, so W1 X1, W1 X1, uh, so minus B equal to minus 3 equal to 0. So X1, so W1 X1 must be, because W2 equal to 0, so I am not writing them, it also equal to 3. So very simple decision boundary you got. This is 3. So this is decision boundary X1 equals to 3. Right. So this is very simple example, which but elegant example. It shows how actually uh, it is evaluated, right? And this could be, if you are taking 1,000 sample, there will be 1,000 equations. But don't worry, they are linear simultaneous equation, and we have already techniques. Computers has program, KP solver has program to solve it. So nothing to be worried. We can solve the uh, support vector machine problem. Okay. So as you can see, um, this is while it can solve a problem like this, it is very quality of solution will not be very good. Why? Because you see, there are some issues here. I have here, I have visually selected these are my support vectors. Now, how to know who will be your support vector? There is no way that you can know them. But what you know is one thing very interesting. You see, I have this one, no? Alpha I, yi. I'm just rewriting it so that you can understand. Hmm, equal to 0. So I have this constraint. If I put the value of w uh, here, okay, if I put the value of w, you can see this times alpha, right? Okay. Now, when the product of 2 becomes 0, say this is x and y equal to 0. So, either of this product has to be 0. If x equal to 0, then this cannot be 0. Okay, this will not be 0. Okay, and this will actually give you important observation that uh, for um, the um, for the samples which are on the boundary, because this is the uh, constant equation constant for, you see, this is a constant for the samples who are in the boundary, right, of the gutter, here. So if this is 0, then this cannot be 0, means the samples cannot be on the boundary. So where the samples could be? Samples could be anywhere. This could be a sample, this could be a sample. This is one good thing, right? So only which are on the gutter, for them only this alpha will be non-zero. Please try to understand again. Huh? Two quantities, 0. We have told that this is Lagrangian multiplier, which cannot be negative. So it could be either 0 or positive. Now, if it is 0, that means this is not 0. And that means the samples are not on the gutter. And when this is 0, this cannot be 0. So alpha, this will be 0. So this will be actually greater than 0. We will have some value. So only for the samples which are on the gutter will have non-zero support vector as non-zero Lagrangian multiplier value. This is very important observation, okay, on the primal problem. Okay, that actually makes your um, calculation much more easier when you have large number of samples. Okay, first of all, support vector machine will not work when the very large sample in the range of million, billion. Okay, it is not a tool for that. But if you have few thousand solutions, right, and you know some handful of support vectors you will be selecting, and somehow your QP solver will calculate alpha. For that, algorithms are there. We will talk later on. So that seeing its value, convergence value, you will know that whether a sample, because sample randomly was collecting, right, selecting and putting it in the constraint and trying to figure out what is the value of alpha. If alpha is non-zero, then the samples could be at the gutter. If alpha is 0, but this is numerical, it never will be 0. So we'll have to do some trick when we learn the algorithms, you will know. But right now you already know what primal problem is, how to solve the problem using Lagrangian multiplier, and how it can give you a result in the form of making a decision boundary. That also you know, seeing this um, small hand problem, right? So here you got the decision boundary. Okay. So I hope that the simple issue you have understood. If not, then please come to the discussion forum and we'll discuss more about it. Okay. With this, I'll conclude. Stay safe. Have a nice day. Bye bye.